And finally, in terms of efficiency, we always talk about training, inference, co-design between hardware and software. One of our most recent works is a VLA, is a vision language model that's right now the best open source vision language model, where we open source the training code and inference code, and even tools how to run this model, let's say in 4 bits on Jetson Nano. Okay, now we are ready for very first presentation from Jason Clemens. He's a senior research scientist at the architectural research team at NVIDIA Research, which he joined in 2013, so quite a long time ago, 11 years. And he did his PhD in the University of Michigan. And in day-to-day life, his research focus is on domain-specific computer architecture, including machine learning and computer vision domains. Yeah, thank you.
All right, thank you, Pablo. And every gray hair you see has been earned over 11 years. Some of these lessons have created some of these gray hairs over time, what we're going to talk about today. Now, when we talk about hardware and DL, there's something very important to think about. In the general hardware, I guess like lexicon, there's this idea of flexibility. You can design for very flexible things. That's where you have the CPU. You can program a CPU to do anything for the most part. That doesn't mean it's going to do it fast, but it'll do it. Then you have GPUs, basically general purpose, but very parallel, very simple parallel processors. We'll get into that into more detail. Do just about anything. Then you move to things like systolic arrays, little compute engines put together in a certain formation so that you can pass compute and do partial computation. And then you get into things like application-specific accelerators. These are things that are pretty much designed to do one type of operation, but do it really efficiently and really well. And then finally, you have this idea of an ASIC. That's really, really hard. It not only does something very well, but it's as efficient as you're going to get because the hardware is specific down to the very much transistor. This transistor does this one thing and you're not changing it, okay? Now, on the other hand, there's this idea of efficiencies, as I was just mentioning. For generality, it's great, but it's not as efficient. So the CPU is on the lower end, then you move across the GPUs. As you get to the application specific, you get even more efficient. And efficiency could mean energy. It could mean execution time. Depends on what your application is. And at the end of the day, you end up at the ASICs with this fixed function. That's as efficient as you're going to get. This thing knows how to do it. It knows how to do it well. And you're not going to get much more efficient in your system than what you get with an ASIC. So let's talk a little bit about these different things I placed on that line. The CPU, jack of all trades, we all use them. They're in your phones, they're in your iPads, they're in your car, everywhere. And the reason is they're able to handle complex instruction streams. You know, whatever you throw at it, it can deal with it. It does a lot of work to deal with lots of different types of flow. So your control flow can be very complex and it's going to handle it and do it well. The memory system in general for some low latency, you know, you have this idea of a cache, right? So if you hit in the cache, it's really quick. If you're missing the cache, it's really slow. So you want to hit in the cache. It's designed to find that locality and get it for you. Usually you have a lower core count, lower thread count compared to some of the other choices we have. But they do have add-ons like SIMD, your vector engines. And most processors today have their vector engine extensions that they try to make more efficient at doing this processing where you have single instruction, multiple data. So you have the same data and you're just doing the same thing over and over again on, not the same data, but you have multiple data and you're doing the same instruction on it. So they're all doing the add. Now, what's interesting is, you know, it's viable for vector codes with limited parallelism, right? If you don't have a lot of control flow divergence in that parallel execution, CPUs can do it in that SIMD operations. Typically you're going to see CPUs be the coordinator. At some point in a lot of systems, there's some sort of small general purpose processor running it, controlling it, telling other things what to do. It is the go-to. It's common. Then comes along GPUs. Basically, the core idea of them, they're graphics processing units. They came around this idea that we figured out that, hey, graphics is a lot of vector math. It's a lot of matrix math. It's a lot of computations that we want to be very good at. So what this is basically Small execution units, lots of streaming multiprocessors. So you have lots of very simple, used to be simple arithmetic units that were put together to do a bunch of compute. And you can actually have different threads or streams going on them at the same time. And these threads or streams can have a little bit of complexity in the control flow. You probably don't want to have as much complexity as like a CPU used to, but you can have some and then they'll still do a decent job. An example for example, the A100 GPU, the Ampere style. And there are newer ones like Hopper and other ones that have been announced. But at the core of it, it's just this idea that there's some small amount of memory, relatively small amount of memory. In the SM, it goes down. You still have a caching system. But one important fact about GPUs versus CPUs, GPU cache systems are designed for throughput, right? We want to grab as much as we can at the same time so we can feed all those parallel threads as fast as we can. Well, I say as much as we can. And we care a little bit less about latency. And so as you get closer, you get more and more bandwidth. So when we look at a full GPU system, and you can see here we're looking at Hopper, they have a lot of units in them. And each one of these units is designed to give us this fast computation and throughput based. We want to push as many computations through as we can, as fast as we can. Everything is built around that, including having custom units now. I'm sure everyone's heard about our tensor cores that exist, designed to do tensor math very fast. We've got tensor memory accelerators now designed to access the memory so that we can do these tensor operations very fast. And we support multiple data formats, even to the point where, honestly, int4 is not on here, but it should be in some of the latest ones. Now, I know I'm from NVIDIA, and I know that we do have CPU chips, we have GPU chips, but there's other DL hardware. We are not the only game in town, and we recognize this. And so one of the things as we go through this tutorial we want to talk about is just general DL hardware. And the systolic array is another common configuration for hardware that's used for DL. It's an array of processing elements. Each one is typically simple. And apparently, yeah. And so the idea is that you have this data flow through the array, okay? So you have this array of compute units. And what you really want to do is you want to pass information along for part of the computation. So what does that really mean? Well, you may start in the upper left-hand corner, and you'd say, oh, the buffer's going to feed some things into that PE. That processing element takes that data, computes something, passes it to its next neighbor while getting something again from the buffers. Systolic arrays like to do compute in a way where they're passing things along. And you kind of wave front through the PEs to get your computation done. Now, there are optimizations that can be done and new operations and things they put in, but simply, this is the most general form of the compute that a systolic array does. And there are many different ones, the TPUs based on this idea, and there's other ones as well, Iris, that come out that use this. Now, we talked about we've not talked about systolic arrays. Let's talk about the custom accelerators. We have one in some of our mobile chips called the NVDLA. And actually, you can actually go look it up, and some form of the DLA is open source for people to use for their own hardware, if they'd like to. Basically, this is a custom accelerator. Its job is to accelerate DL models. It's configurable instead of programmable. What's the difference? In a program, I give you a set of instructions. Say, do this, do this, do this. In a configuration, I say, that operation you're going to do is going to be this big. You're always going to do that operation, but this is how big it's going to be. Okay? Configurable is basically saying, I have a subset of things I can do. You're going to tell me how big or which one to do. Programmable says I can make you do anything. And NVDLA is more of a configurable thing. It is targeted for inference, although there's work to make it expandable beyond that. And custom accelerators require so much work on a software ecosystem. Anybody can tape out a chip with an accelerator on it. Making that work well in your software ecosystem, that's what it's all about. That's where the real work occurs. And you'll see these things used, these accelerators, in places like edge inference, right? Your smartphones, they have things called NPUs. You have the NVDLA, you have these things. Our Orin systems have this. They're used there because they're typically more efficient. right? We talked about the efficiency curve. Used in places where efficiency matters a great deal. And this brings us to the wonderful world of system on chips, which has become very popular and very common, especially in a lot of different compute systems today. You look at what's going on in a lot of systems, you look at what's going on in Apple's chips, even our Jetson chips. It's basically take a mix of CPUs, GPUs, custom accelerators, put them together, share the memory system, allow them to talk to each other. Part of the reason you have this is because most full applications aren't just one thing, right? What's the point of doing inference if you can't tell the user what it means? You know, if you want to actually display the result of your segmentation for someone to see, well, you actually have to generate that display component as well. And so SOCs are an excellent way to put it all together and try to get it to work as efficiently as possible. And it does require a much more complex management system. How do you decide where you're going to run something? Should this be running on the CPU, the GPU? Should this run on the accelerator? How do you make them talk together? How does the accelerator tell the CPU it's done doing that inference it was told to do a little while ago? These are all things that have to be worked out, and these are all key factors in deciding which system on chip you want to work on, and this is what a lot of the stacks try to deal with in the drivers. Okay. And I'm not sure why it's not moving forward. I appear to be stuck on the slide. No, it's gone.
Time for a question while we wait?
Sure, go for it.
Tensor cores, are those essentially an ASIC embedded in terms of the architecture?
The tensor cores are not an embedded ASIC per se, but they are a piece of hardware that is very optimized for doing matrix multiplication. I would not call them an ASIC because of how they operate. So without getting myself in trouble, that's about all I can say. It is tough. So,
question. So the systems on chips that you showed, where CPUs and GPUs all have a lot of common things. So is it the cache that you're talking about? Is the memory cache the same for CPUs and GPUs in that, or is that separate? Or what are the things that are common? Like, why is it faster?
okay. So let's talk a little bit about how things are executed on a GPU versus a CPU in a typical discrete system, right? In a typical discrete system, you're going to talk over some sort of interconnect. PCIX, right, is common. So the way that typically works is you're actually transferring things from system memory over PCIX into the GPU's system memory. So the CPU's memory is talking through PCIX to the system memory that's on the GPU. Now, when we talk about an SoC, there is no longer two separate system memories. Turns out the CPU and GPU system memory are both the LPDDR or the RAM that is sitting there. So you've actually gotten rid of that transfer, right? It's actually more efficient because you no longer are just saying, hey, go get this, you're actually saying, here's a pointer. It's already in memory. Go get it. So they're actually sharing the system memory typically. Now, whether they share the caches,
It's not.
honestly, that is an implementation detail that depends on the provider, but it is an open research problem how to properly share caches when one of them is throughput-based, the other one is limited.
Switch laptop.
All right, looks like I'm switching to my laptop. So
Do you have an idea of what are the typical latencies of moving, for example, an image from RAM into GPU memory?
honestly, off the top of my head, I don't, but if you wanted to figure it out, you could look at the PCIe, depending on what type of PCIe you're using. You can look at the bandwidth that it typically runs at. It's typically not super so that plays a role. Now, there is for NVIDIA, we've worked on things so that can happen behind the scenes and kind of happen for you. You know, if you've heard about our ability for you to just malloc and then the system just works. So stuff like that. But yes, there is an overhead. You're going to do OS system calls and things that you're going to take a hit for those transfers.
You mentioned about how the software ecosystem gets really complicated when you're starting to venture into realms like systolic array or ASIC. Why is that the case?
Well, at the end of the day, you've got to find a way to talk to a system that is used to having direct access to components like registers, right? You don't necessarily have an easy access to all the information that's going on in systolic array or everything. You're usually talking to a little controller and you've told it to go, okay? And then it's got to return back. So at some point, you've got to synchronize we like to use. And what this is about is, remember I talked about sucking through the what that saves you is you don't have to pull as much memory bandwidth. If I get to reuse an element like 20 times before I have to fetch a new one, oh, that's fantastic, because now my bandwidth has to be 20 times lower, right? As long as I can keep it fed. And so that's where arithmetic intensity comes into play. It is trying to figure out, for every byte of compute, or how many flops am I doing for every byte of compute fetched? And when you start thinking about the hardware, you start doing things like this, where you're basically trying to figure out, let me compute the flops in this layer. And if you Google, you'll find a bunch of things from the old school days about doing it for convolutions. You can find ways on Medium to do it on transformers, but the core idea is very valid, which is I can basically look at the type of layer, and we're going to talk a little bit more about this in a minute, and figure out how many flops I think that's going to take. And based on the sizes of it, I can estimate that. And you can even use tools like TorchInfo and things like that that'll give you an estimate. Although I will give you a hint to be wary of some tools. If you are using a framework to run a network, some tools only look at the calls to the convolution module, not to the functional call of convolution. Which means if someone put a model in that framework and used f.conv instead of using init.conv, it doesn't count. So some of those particular counters will actually not tell you some of the flops that are actually being used. And this is just a lesson. I mentioned the software before. Pay attention to what's in the software and how it's doing it, and pay attention to what you actually expect. And this is also why being able to do this by hand and figure out if you're like, why am I missing like 3 million flops? Well, that's probably what's happening. And you can then take that and take your hardware configuration and say, hey, if my thing has a compute bandwidth of 1 TOPS, then I can figure out the best case scenario for my compute would be 44.8 nanoseconds, right? Now, keep in mind the keyword is best case. There's always going to be overheads. There's always some derating factor, right? But what you want to do is be able to use these to figure out, are you in a realistic place? Are you bounded by something? And so let's understand performance a little bit more. Math limited, okay? Basically is the equivalent of saying, hey, if I could, basically, if I had more compute units, this thing would sing. It's like, yes, give me more compute units. That just basically means I don't have enough compute units to go in there. Memory limited. Basically, we can't, the straw analogy again. The straw is only so big, the pipe's only so big, I can only get so much information. While the compute utilization is not very high. Basically, the computer, you might be like, I'm only using 30% of my compute units, but I'm using 100% of my memory bandwidth. If only I had a faster memory chip. And so these are just some general ideas of, using this intensity for estimating these limitations, math limited versus memory limited. And you can see here some examples of what you might classify things as. And we're going to talk about in a moment some ideas of dealing with some of these issues, depending on where you sit. But one of the things I wanted to note is that you end up in this quadrant type system, okay? If you're in the upper right-hand corner, if you have high memory bandwidth and high compute bandwidth, you're like, I'm 80, 90% in both, congratulations, you got some good programmers. If you are in the upper left or the lower right, there may be some things you want to do. Your memory limited or your compute limited, and depending on which one, there are some things you can kind of look at. If you end up in that red corner, that's because somebody basically downloaded an example. But in truth, that just basically means that this code is very unoptimized. And from an architect, don't come to us and tell us, oh, this hardware sucks because of my unoptimized code. Okay? I will not tell you how many times it has been, oh, well, did you do this thing or this loop reordering? Oh, why are you not turning on these abilities inside your code? That's how you end up in the red region. Now, every once in a while, I'll admit, someone ends up in the red region because they came out with a very new application that we never saw coming. Doesn't happen often. All right. So now let's talk a little bit about DL performance on GPUs. All right. We're in a room full of people who I pray all understand that a lot of DL is matrix multiplies. The gem is the heart of a lot of different ways of executing this. And what's interesting about this is if you look at this formulation, the gem is just defined as C is equal to alpha AB plus beta C. Everybody's used to seeing that. These are matrices. This is what we're going to do. Okay? And commonly, C is a pre-existing matrix that you're going to overwrite your output to. All right. Well, if you look at this, let's break it down a little bit more about math and memory bounds here. Matrix A, is an M by K. Matrix B is a K by N. C is an M by N. Everybody still back in their linear algebra class? Remember what it was like those first few days? That's still valid. Now, what comes up interesting here is we're going to talk a little bit about something called fuse multiply adds, FMAs. That's versus flops. And this is something that gets kind of wibbly wobbly for certain people depending on who they are. Okay, so a fuse multiply add is actually two operations. You do the multiply and you do the accumulate in one. And there is a lot of hardware that has a fuse multiply add instruction. Okay, now when you start talking about the flops of your system, typically you have to multiply the fuse multiply adds by 2 because 2 things took place. Each fuse multiply add actually did 2 operations. Okay. And also note, alpha and beta, if K is large enough, they don't matter. But now let's talk about this arithmetic intensity a little bit. If you look here, and you look at the number of flops over number of bytes accessed, and I just want to be clear, this is a model of number of bytes accessed that is arguably a little bit idealized. Just go with it. If there are any architects in the room, yes, I realize depending on caching and tiling, other things may be different. But at the core of it, in this idealized world, you look at this flops per bytes accessed, and for a tensor core V100, you end up with these different ratios. So if I look at this, if the matrix is n by k, it's 8k by 128 by 8192, that's memory bound. We just are trying to fetch a lot of memory. We just can't keep the things in. On the other hand, if we get enough data to chew on for this matrix multiply, and we can reuse it, the reuse, we talk about the arithmetic intensity is really a measure of reuse. When we get a big enough size, 8192, out in the middle, now we've got enough that we're reusing stuff enough that we're not fetching all the time and running out of memory bandwidth. Now we can actually just get down to the grinding of the compute. And now if you had more ALUs, you could speed it up. And so when we talk about this, if you look at the multiply adds per clock, right? For flops, you multiply by 2. If you take the A100, 108 SMs, 1.41 gigahertz clock, you can actually get the numbers that people advertise. In this case, I'm using NVIDIA's advertisement, of course. But for any hardware system, you should be able to get how many compute units, what is their clock frequency, and therefore you should be able to compute how much compute they have available at peak, ideally. And so if you look here at this table, it gives you some idea. And some of the things to take into account, like in an NVIDIA system, you have the CUDA cores and the tensor cores, right? And the tensor cores are specialized for MMA. So, yep, they're more performant. Now, once again, if we go to Hopper, so we jump to the current, this is actually an H100, not the H200, but you can see we end up with these nice, massive teraflop numbers for depending on your data type size. And that's going to come back later as an important factor. Do you need 32 bits in your application? Probably not. You'd be surprised at how many things work at FP16 or INT8, or according to some hardware papers, 1 bit, but you know, depends on who you ask. So let's talk about how our GPUs are really doing this matrix multiply a little bit. We're tiling it, just blunt and simple. We basically are gonna take the input and output, split it up in the tiles, and do patches of the output. You're gonna tile the work. So you're gonna take this thing and you're actually going to split it up based on the tiles. So whatever your input size, your output size, okay, this is the size of my tiles. So this number of tiles, and we're gonna send those off to be computed on. Well, that means that there's a couple of things to take into account. One, having a good tile size is important. So this particular piece is just showing something very important. The one on the left, I just want to show the importance of using the newer version of any software. Remember I said unoptimized software? The graph on your left and the graph on your right. The difference between those two, or I say on the right, but you know what I mean, the middle one. The two graphs, one of them used version 10, one used version 11 of a library. But I will note some things interesting in that graph. For example, when things are divisible by 8, performance gets better. That's because real hardware has finite sizes, okay? So as hardware people, we're gonna say you only have 8 of these, 16, 32. Yes, we love powers of 2 because it makes the hardware easier to deal with. And so you're gonna see that. And as such, if you look over here, if you can get the tile size that matches what our hardware likes, you get peak flops, right? Same problem, just retile it. Make things run more efficiently, okay? Or more importantly, make the size such that it is efficient. And let's talk a little bit about why that is. And A and B here actually kind of explain. We're going to split the problem up into tiles, okay? If your tiles line up perfectly to the size that we want it to be for the hardware, we launch it, everything gets finished. In this case, let's say we were able to do, let's say every column was a wave of computation. It takes us 2 waves. However, if you make your size just a little bit bigger, you're like, oh, I can just get a little bit more learnability from this layer if I could just increase it just a little bit, but you decided to use a non-power of 2 or just a size that just isn't great. That now takes 3 waves. And that's why when you look to the graph on the right, when we look at the size of n, once you go over the size, basically a quantization effect. It's like, oh, it's pretty flat. And then all of a sudden you jump up and it takes longer, regardless of how much you add and jump up. That is an effect of you just went past where we could compute. So you got 2 choices there. Either shrink your layer, or, hey, if you don't care about energy or anything, go ahead and use the rest of the compute in that layer. Why not grow the size of that thing? Assuming your memory bandwidth allows you to. So, and this goes back to that wave quantization thing we were talking about. The total number of tiles. The tiles are basically split out to work across the GPU. The amount of workhorses you have determine how many waves of compute you need. If you are basically not fully filling up the GPU, you got to ask yourself, how important is that? Should you A, just go ahead and fill it up? Or B, should you find ways to shrink things so that you take less work? Okay. Ideally, your utilization, the best utilization is always going to be some multiple of the hardware's capability. Try to get rid of those tail effects. Now let's talk a little bit about DNN operators in general categories, right? Element-wise operations, they're each independent. They tend to be memory limited. You know, they perform very few operations per byte, right? I'm talking about an elemental add, elemental multiply. Reduce operations. they're usually arranged over the input, right? There's some set that's being there. We're talking about pooling, batch norm, layer norm, softmax. They typically also have low arithmetic intensity. You're not doing much math for the data you fetch. So you're going to be memory. Dot products, well, they can be very much math limited if the sizes are large enough. Okay, so fully connected layers, attention layers, convolutions. Depending on the sizes that you have within there, you could be math limited, you could be memory limited. It depends. It's not everyone's favorite answer, but it does, but could be. Other transform example, tensor contractions, right? You know, linear layers, statistical norms. These are all things, if you look at your flops and your runtimes, you know, element-wise ops, these are all operations that, you know, you can carry and you can try to figure out, you know, percentage of flops versus runtime and things like that, as you see on the right. So as you run through these various pieces, right, you can look at what's commonly used to figure out, well, is this going to be compute? Is this going to be memory? Do I have a system where my memory bandwidth is limited? Should I be worrying? Should I be doing more with it? Should I eliminate these operations? So now, one of the key things here is how to find a problem. One, Google, find out how big the hardware is you're running on. Determine, you know, the bytes per op that you should have. Compute the arithmetic intensity. Determine if there's sufficient parallelism in the GPU by estimating. You know, this problem is going to be broken up. And yes, you can find documentation on how we do matrix multiply in the GPU and how we do the tiling. And you can go look that up and get an estimate yourself. You know, most likely performance limiter, if there's not sufficient parallelism, probably lazy. It could be math limited if there's sufficient parallelism. There's intensity, you know. It could just be like, hey, I need a bigger GPU. I need that 4090. You know, it could be, you know, memory. If there is sufficient parallelism, the intensity is lower than the GPU wants. It's just like, hey, I just don't have the bandwidth. So here's some recommendations. If you're operating in the math limited regime, if the speed of the routine is limited by the calculation rate, performance can improve by enabling the tensor cores. As I mentioned, they're designed to do MMA or do matrix math faster, right? Enable these things. Use a piece of the system that is more efficient at the compute, that gives you more compute per time. Make sure that your shapes kind of match what the tensor cores want, okay? Don't give the tensor cores inefficient shapes. Choosing parameters to maximize the efficiency. Divide the work between parallel processes if necessary, parallel GPUs, and figure out how to divide it with numbers that match what the hardware is expecting. So you have a hierarchical model. You know, for memory limited layers, usually the first couple layers, because as we know, it's coming in there, there's usually a lot of compute. They can take up a lot of memory in the front end. You know, dense convolutions are common. Or use dense convolutions. Go ahead. You don't have to sparsify the first layer necessarily. Use that dense. Minimize pooling. Avoid layer norm. Pablo mentioned it. Layer norm requires you to go over the data and go back over the data. Try to avoid that. All right. And you know, use something like batch norm. Turns out you can, for those that don't know, you can fold batch norm into like convolutional layers at basically no extra cost. Systems love it. For math limited layers, you know, as he said, usually the later layers, depth-wise should be fine. SE works. You know, layer normalization doesn't hurt that much anymore. All right, I'm gonna tell you this from a hardware person's perspective. We love ReLU. ReLU is straight up a bit check. Is that bit 0? If it's 0, pass the data on. If it's not, make the data 0. Or vice versa. Let's see. If the bit is on, make the data 0. If it is off, pass it on. That basically tells you if it's negative or not. ReLU is fantastic. Anything that's not ReLU, you're paying for it. Even if it's just a lookup table. And pixel shuffle can be helpful for large images. Tensor cores, all right, talking about GPUs, but any system that is designed for something specific or has a customized unit that is designed for or data type, just use it, all right? FP16 should be a multiplier of 16. Remember I was saying make the sizes the size you want. In 8, multiplier of 32 for the sizes. Mini batches be a multiple of 8. Make it hardware friendly. And I tell you this because most software stacks are designed, you did make it hardware friendly, I'll find a way to make it work. That's where your performance cliff happens. That's why you show up with the unoptimized code and someone says, did you even try? Because you've run into that problem. And so you'll see this example here that, well, concatenate matrices for the transformer. In short, these ideas, when these are followed, you see improved networks. How many people out here have released a network or seen someone release a network and then release V2 that's faster? And yeah, there's typically a novel idea there, but there's also typically a lot of, we optimized it by changing this size or making it better for the hardware like this. It happens in a lot of V2s and V3s. For convolutions, layout choice. If you're trying to use the tensor cores, the tensor cores are basically, they want a specific order. If you don't give them that order, either A, your data has to be translated to that order, overhead cost, or B, you're not gonna run out of tensor core. Someone's got to give. And, performance of forward convolutions, this is just showing you making things a multiple of things improves it. Notice when it's a multiple of 8, you see the dip in the graph, right? Every multiple of 8, dip, because they listened. Linear layers, make the multiples of 4 to run efficiently on the tensor cores. For A100, if you don't want to use, you can be divisible by 32 for different data types. Large value of batch size inputs, outputs, improve parallelism efficiency. Basically, fill the GPU, all right? This is the heart of that to some degree. If you don't fill the GPU, you just have idle things sitting there and you could be having more performance. And if you look here for transformers, and this is just some of the interesting things that we have here. If you look here, one of the key things that we're looking at is if you look at the top left or top right, I guess from your perspective, right? I mentioned before, use the latest software. From one version to the next, perf boost. We hire a lot of smart people who find out ways to make our hardware very, very fast using software. And we release that in our libraries. It's just the truth of the matter. And every company who releases hardware is doing that. And if you take a look here, once again, the different sizes and the feed-forward layers, you should see improvements. Okay, let's just make things a multiple of 8, please. All right. Mixed precision. I've said it a few times. Do you need FP32? Mixed precision basically says you don't need it all the time. Things can be lower bit width and give you a perfectly good answer. So take advantage of that, okay? And mixed precision, if you turn it on, will work a lot of times. And if you turn it on with their wired library, they'll do some things like, hey, take care of that shifting of the histogram for you automatically. And so the heart of it is you don't typically need the full range of FP32. I understand when you're first developing this new architecture, you want to get it out there, you want to figure out if it works, fine, I get that. FP32, I get it. Well, one of your first steps should be before you release it, figure out does it have to be FP? Can it be FP16? You want to be in that top of the charts for who's the best performance. Use some mixed precision. Use some quantization. Use data types that you need to. And what's very interesting is, you have these different dynamic ranges, right? So there's FP32, there's TF32. Figure out what you absolutely need to use. Because there are benefits to using different data types that can be more efficient in the hardware and on the systems. And if you're using something like an NVIDIA container from NGC or whatever, guess what? TF32 is in there. It's ready to go to trial. PyTorch has ways to turn on mixed precision. This is just an example of really quick, you know, how to use it, backward passes, autocast, backward pass. I'm gonna zoom past this. Our slides will be available online for people who want to look at this code in detail. I'm not gonna step through it. I assume everybody sitting in here, unless they're a manager, can read the code. Sorry, managers, can read the code and understand how to use it. Some things to note. Hey, you want to know if you're using tensor cores? Right? You can actually check. Built into the profiling already. It's available. Figure out if they're on. All right. One other thing I want to talk about is this idea of structured sparsity. And this is actually available. You'll see it in A100. It's continuing forward in H, which is there is this idea that you can have a structured sparsity where a fraction, half the weights are zeroed out or set to zero, and you can still get good performance. Okay, and it's all a part of various libraries that you can look at, that you can find, that turn on this sparsity. And so think about that. If I kill half the weights, that's less stuff I gotta load, and that is less compute I gotta use. So it's just to summarize these hints to some degree. You know, we've talked about most of this stuff. Move to different numerical formats. Rework your algorithm. Use structured sparsity. Use the specialized hardware. And talk to the specialized hardware the way it wants to be spoken to. The specialized hardware does not like being disrespected. When you disrespect it, you don't get the performance you want. You know, if you're in memory bandwidth, look at the formats. You can overlap memory transfers. You can restructure your data, resize the problem. You know, lots of things you can do. And just a note about the different sizes of GPU memory and the way things are used. Just in general, when you look at how your model uses memory, this goes back to like Atom versus Atom W. Okay. Turns out if you do the math, Atom W uses less memory, right? One thing about training a model that you've got to take into account, your optimizer counts. It's sitting on the GPU, right? Any of the extra stuff. It's not just what's in your base model. It is everything necessary to do the computations for that base model. So when you're trying to figure out, you're trying to use every ounce of capability for your model, take into account your optimizers. Be more efficient with them. Choose the optimizer states and that will allow you to get more model in there as opposed to optimizer state. And for those that need a refresher about different types of parallelism, data parallel, okay? It allows you to speed up training, right? You basically say, hey, what I'm gonna do is I'm gonna have everybody doing a compute, we're gonna average it, right? Or you can do model parallelism, where each GPU is running a piece of the model, and you exchange the data. And even with model parallelism, you know, you can do it in multiple ways. One way is to say, hey, front half of the network is one place, another next part of the network is another. You could also say half of this layer is one place, half of this layer is another place. All legit ways. Which way is best for your model? Kind of depends, and depends on what you're doing. And then you have things like gradient accumulation, right? Where you can basically, to split the batch into, or split the batch of samples and share the information. And now we're coming to some of the last few things I want to talk about. TensorRT. What is it? It is a toolkit for NVIDIA GPUs that allows you to optimize your networks better for NVIDIA hardware, is the heart of it. It has a lot of different pieces. But what it can do is it can help you do quantization. It can help you get it ready for the DLA if you want to use it on a DLA hardware. It can get it ready for the GPUs. You can produce ONNX models. It can do a lot of different things. And so, you know, at the end of the day, I would recommend, if you're going to, one of the first things to do is see what TensorRT can do for your model. TensorRT gets you a lot of speed up by using a lot of the rules and rules of thumb that we have learned internal at NVIDIA. Okay. And profiling tools. NVIDIA has profiling tools. You don't just have to use what came in PyTorch. You don't just have to use what came in TensorFlow. We have tools whose entire job is to check out the performance on the GPU. So what does that mean? That means they understand every bit of GPU code that's running, not just what's in PyTorch, right? And they can actually take a look at what the CPU is doing. And as a matter of fact, if you look closely at what PyTorch does, it actually calls our profiler at the very bottom, if you look closely, if it's on. So, but we have different ones. We have Insight Systems, Insight Compute. Okay? Systems gets you the system level. Figure out how much time these kernels are taking. Figure out where all your execution time is going. Insight Compute can get you in there and say, hey, exactly how many fuse multiplied 32-bit ads was run. Insight Compute can tell you. There's no guessing. It can get you how much of your utilization, how much your tensor cores. And you get nice visualizations like this, a GUI that you can click around and see how good things are. Or you can do command line like we architects like to, so you can get a CSV file out so that you can process that data and use Matplot to generate just so many different things. Say, look, we need this widget. And you can generate your stats. Okay. Once again, these slides will be available online and you get these nice GUI graphs. And this is compute. As I said, you can use these commands to get very specific data out. And another thing to note, if you're doing GPU code, and you may need to do custom kernels to get full optimization, because if you've got some weird thing that we haven't thought of at NVIDIA, you may have to write the CUDA code yourself. You can even profile that with MVTX regions, which you can actually put it in Python and profile. It also works in C and C++, which basically is named regions by you, the user, to find out what's going on. You know, at the end of the day, there's a lot of profiling things you can do. I will say, when dealing with architecture, we do something called locking the clocks for comparing performance. For those that aren't aware, if your GPU gets hot, it slows down to prevent blowing itself up. So what we do is slow down to prevent overheating, probably long term. But what you can do is you can tell the system, hey, the GPU lock the clocks. Don't use your algorithm to figure out what the clock should be, because here's the problem. If you run one model and the clocks aren't locked, and the algorithm says, oh, I'm gonna, based on my current temperature, I'm gonna let the clock go up to this high. But then you run another model, but it decides, oh, well, the GPU is a little bit warmer now, so I'm not gonna let it have the clocks as high for as long. Well, was that a fair comparison if you're using, anything that involves time? The other one took longer because the clock was slow, partially. And so you want to do things like locking the clocks, releasing the clocks, considering what's running in the background. Just be wary of just running it flat out on your GPU and saying, look, this is my performance. And that brings me to the thank you slide.
Thank you, Jason. Any question? This slide. You mind repeating the question?
Leather jacket.
Okay. Is there like a profiler tool where you can just reproduce these green graphs that you showed with the dips? For example, like the profiler called this TF Live model, give me the latency.
The irony is you can use the different profilers I've shown you to get that by pulling out the latency of your kernels. Yes, in short. The thing is, there isn't just one profiler. About the question was, is there a profiler that can give you the graphs we saw with the dips? And I guess the point is that there are so many multiple ways to get it. I don't know if there's a simple button to do it, but there are ways to get it that's relatively. Just any profiler, like we talk about Insight Systems, it'll tell you how long things took to run, right? So all you would do is basically execute and figure out how long it took to run for each instance. Yes. You mustache. Sorry. Yep.
So I was following what you talked about how you would tail effects with that quantization by using multiple two, and if you get past that breakpoint, you might as well just go up to the end of it. But then when you mentioned taking into account what optimizer you're using, it's like also sitting on those two have anything to do with each other, or does the optimizer not affect the type?
That is a great question. Yes, since the optimizer is running on the GPU, it's going to take it into account. But if you think about the optimizer size, it's usually related to your model, right? So you will be able to figure out its sizing appropriately.
Any other question, please?
Most data types are naming convention, right, in a FP32 to FP64. The number indicates the size of the data type. So there's this what is it, the tensor 32? Is that actually not a 32-bit data type?
It is a 30-bit. All right. The question is TF32 a 32-bit data type? It is, but they've changed the representation slightly to be more efficient, and you can look more about that as well. Or I say more efficient, to be different. It's more tailored to the application space. That's it. So if for those that aren't aware, FP32 is an IEEE standard, basically. And so they're like, hey, we don't need everything that FP32 has in the way that it does it.
One last question, please.
TensorRT does its best to try to make the GPU full, but it's still going to go with whatever size you gave it. All right. So the question was, does TensorRT make sure the GPU is full? It does its best to efficiently map it to the GPU, but it's constrained by what you.
Let's thank Jason again. We're running a little bit behind time, but still now Jason has been talking about hardware, and now Main is going to talk about, from the software point of view, how can we train and do much better and generate better models that run better in our hardware. Main is a senior research engineer at NVIDIA. She has been working with us for about 4 years now. Since the first day, she's working on neural network acceleration with really good algorithms in compression, pruning, quantization, and with a very nice experience also to bring these algorithms in the car. So please welcome Main.
Okay, thanks, Jose. Yeah, so I'm Mayin, and for this talk, I'm going to talk about the neural network acceleration if you are given a large model, so that's like how we can compress the model to accelerate. Yeah, so this talk is about deep learning and the networks. As you know, like there has been a trend of exponentially increase the model size over the past years. So this graph that you can see how this trend looks like. With the emergence of the transformer GPT large language models, actually the number of parameters of the model has been like increasingly in a large amount, and even increasing to like 1 trillion. So such a kind of model will lead to very huge energy consumption. And like when you deploy kind of this kind of large models onto like different kind of platform, this could become a very challenging task. For example, when you want to use this kind of model in the edge device, directly importing this kind of model would be infeasible because there will be like limited storage and memory on the device. And for some kind of applications on the edge device, they usually have the real-time requirement. So you will be need to compress model to make sure that this is efficient. Sorry.
This is what
okay.
I have a difficulty with Zoom with seeing it for there.
Okay. Wait. So how can I stop the presenter view? Actually, I do this. I cannot. Yeah, I cannot.
You need to go to PowerPoint again, but you may not be able to see.
You need your
Or share in
notes.
different way?
Yeah, just start PowerPoint, but not yeah,
This one?
Can you check now?
Does that work? Okay. Yeah, so back to this, like deploying this kind of model will be quite challenging. And when it comes to the edge device, I just mentioned, like for the real-time systems, you probably need to compress the model to get a more efficient inference. So like you can get the real-time response. And even when it comes to the cloud computer, when there is a large amount of compute capacity, you still like want to get it faster because there is the complex concurrence. So you want to make sure that your service is always online for more users. So to deploy this kind of model and make it efficient, we need the model compression here. So why not directly from the content model? Well, that's actually like for the larger model, you will have the larger capacity of the model for learning from the data array. So if you directly come from the content model, it's highly likely that the model is going to be harder to train, especially like the task is more challenging. So we will usually like start from the large model and try to compress it to preserve the accuracy of the large model. And in this talk, we are going to talk about like the two common techniques, which is quantization and pruning to help us to get a faster model inference. And as we just mentioned, like for nowadays models, they likely to be very huge. So it's highly likely that a very extreme compression rates would be needed. So we are going to talk about how we can achieve better latency and accuracy trade-off for large size, for large compression, for large models. And on the other side, when we compress the model to make it more compact, we would also need to carefully take care about the model robustness, because we will show later, like when we compress the model to a compact one, it will generally like hurts the out of distribution generalization. So it's going to be a trade-off between the generalization and the model compactness. And here we are also going to talk about like how we can do the pruning in a robust way. Okay. Yes, sorry for that. Or maybe let me try with my own voice. Can people behind her hear me actually?
Can you lower the volume from there, Pablo? Yeah, that was good. Can you try?
Okay, test. No, no sound. Test. No.
Yeah, now it's coming.
Coming, okay. Yeah, let's continue and start with the quantization. Okay, so when we train the model, actually, we typically train it in 32 bits, or sometimes we use mixed precision, like mixed with FP16, right? But this actually could help us to train the model because it can take advantage of a wider range of the numbers during the training. But when it comes to the inference, actually, if we use the model, if we represent the model using a lower precision, for example, like in 8-bit or even 4-bit, actually the model size can be like reduced and the inference can be accelerated a lot. So here as an example, like if we convert the 32-bit model to 8-bit integers, it will result in like 4 times memory reduction and about 2 to 4 times throughput improvement supported by the NVIDIA Tensor Core. And for the large models, we potentially even would consider to compress to 4 bits. And actually, like this is doable now because we have NVIDIA has the new GPU, which is supported by the Blackwell architecture. So this, such as like DriveThor. So this kind of GPUs can help, can support the 4-bit floating point calculation. And as an example here would be for the Llama 7B model, it can achieve 9 times improvement when we compress into 4 bits. So like we can further increase the inference speed of the models. To quantize the model from the high precision to the low precision, because the low precision actually can present much lower number of values. So we need to kind of like map the values from the high precision to the low precision. So we need a mapping process as we show here. But the key here would be like how we can get a proper scaling factor to scale down the value from the high precision to the low precision. But what is a proper scaling factor? But if we look at the quantization process in closely, then we can see that actually the quantization process is, as you can see, like from the upper bound, like this is the original grid with the original value. And with the scaling factor, the values actually are mapped to a lower precision. And as you can see, some of the values are actually mapped to the same value after the quantization. If you can, so like for these 2 values, they are mapped to 1 value. And for the values that beyond the limit will be clipped to the like the values limit of the low precision that can present. So now if we dequantize this kind of values to the original grid, we can see how this error comes in. So, and with different kind of scaling factors, the reduced error will be different. So the optimization goal of the quantization will be to like, we choose a scaling factor that minimizes the total loss induced by the quantization for all of the parameters. And there are actually different kinds of algorithms to solve for this problem. And for example, like in our previous CVPR work, we proposed the generic algorithm that work for different kind of codebook, like int8, int4, or even FP4, where we optimize the scale factor and the value assignment in an iterative way to get the optimal solution. So here are the link will be provided, like, and you can check more details if you are interested. Now we know how to quantize the value from high precision to low precision. Then the next question would be like, how can we quantize a model in practice? I think like the simplest way is that you can directly do the post-training quantization, which means that when you train a model in a normal way and get your trained model in FP32, and then you directly apply your quantization algorithm onto the weights. So you can quantize the weights into a lower precision that you desired. But now here comes the question, like, how can we quantize activation? Because activation, you cannot get that from the saved model checkpoint, right? So here we need to get some representative data so that you can get some distribution data of all the quantizations. Then use those kind of distribution data, you calculate what kind of scale value would be optimal for the activations, then quantize accordingly. And such a kind of quantization method is quite simple and fast. And it does not involve any training process. But it's also because it does not involve any training process, it means that it does not consider the effect of the quantization during the training. And after we quantize them, it is highly likely that the accuracy will drop a lot because of the quantization error, especially like when we quantize into lower precision like the FP4. So here comes the quantization-aware training, which aims to like compute the scale factor during the training process. In specific would be like for a given model, we can insert some fake quantization operations into the graph node. And as you can see here, with this quantized and dequantized nodes inserted, it's going to be mimic the quantization error during the training process. So the training process will going to be adapted to the quantization operation, and the trend presentation will definitely be more robust to the quantization, right? So at the end of the training, we can just directly use those saved scale factors to help quantize our weights and activations. So to summarize, would be like, while post-training quantization is simple and fast, we actually would more recommend for the quantization-aware training, especially for the large model compression in FP4 to better preserve the accuracy. Yeah, so that's for the quantization technique. And the other commonly used technique would to compress the model and get the acceleration would be to prune the model. Yes, I think like for nowadays models, they typically would be over parameterized, right? So what a simple way to prune the model would be to directly remove the single parameters from the network, where we identify like which kind of parameters would be less relevant to the output. Then we remove those. This kind of model, this kind of pruning is going to lead to like networks with sparse matrices. And we are going to do some sparse matrices calculation. And it requires specific hardware to support, right? So actually, like when it goes to the actual acceleration, sometimes it's going to be hard. But there is the special case, as also introduced by Jason, like we have this ampere sparsity, which like we prune two parameters out of every 4. This kind of structure will be supported by the NVIDIA NPN tensor core, sparse tensor core. Then we can get half of the memory and inference up to like 30% of the speed up. Then that's up to 30%. That's not enough. So here comes a more coarse-grained way to prune the models, where we perform the pruning onto the entire channels. So like we identify the less relevant channels and remove the entire channel directly. So it's going to make the layers slimmer and directly lead to a smaller network. So common GPUs can take advantage of the acceleration, and we can potentially get a larger inference speed up. And there involves many different kind of algorithm to achieve channel pruning. And yeah, let's talk about more, because from the literature, the methods can be categorized into different ways. So one of them would be regularization-based method, where you add a regularization onto the training process to constrain the parameters that are less important to close to 0. So during the training, you push the less relevant parameters to 0, then you, at the end of the training, you can directly remove them without causing too much loss perturbance. Another way is to perform in meta-learning based method. You can leverage some hyper networks to predict the weights parameters for the prune network directly. And another common way would be saliency based, where you predefine some saliency metrics to measure how important a parameter is or a channel is. Then we remove the less relevant one, the least important ones from the network. And I think like we are going to talk more about the saliency-based method here as a as a method to help illustrate like how we can better preserve the accuracy and the model compactness trade-off in this talk. And here we provide some links to the to introduce for regularization-based method and the meta-learning based for you to know more in details. So for saliency-based method, as I just mentioned, it uses a metric to get score indicating how important a parameter is or a channel is, according to how much it will induce the loss perturbance to the output. I think like here, the magnitude-based method is quite intuitive because if the model weight is small, close to 0, which basically means that the output of that the output induced by that weight is small. So even though you remove those weights, the output of that neuron will, or that parameter will not be impacted too much. And the other commonly used criterion is gradient-based method, where the importance of a parameter is measured directly on how much loss change you could get by deleting that parameter. And this is actually shown to be more reliable than magnitude-based method because it's actually measured directly on the loss change, right? So one example would be the Taylor importance. Like we model the importance of a parameter to be the loss change caused by setting the parameter to be 0. This kind of setting the parameter to be 0 is mimicking the process that the parameter is going to be removed. So, and you can see that this is going to be similar to adding a perturbance to the model weights. And the loss change or the importance here can be approximated by the Taylor expansion in the vicinity of the weights. And as you can see here, if we take the first order of the Taylor expansion, the importance can be calculated directly from the model weights and the gradients, which is easily obtained during the normal training. We can also choose the second order expansion, which leads to the optimal brain surgery idea, which was proposed quite early actually. And the importance will be measured by the Hansen matrix. But in practice, Hansen matrix calculation can be quite calculate intensive. So in our previous work, we found that actually the first order importance is already good enough for promising accuracy. And you can check we provided the link to the paper for you to check more details about the accuracy comparison. But the summary would be like the first Taylor importance score will be good for the model pruning. But that's for the importance for single parameter. And when it comes to the channel pruning, or we say neuron pruning, we can basically it's a group of the parameters. So we can simply measure the importance of a channel to be a joint importance from the parameters. And if so, basically just taking the sum of all the importance of all the parameters and sum together as a square or as a 2 norm or the absolute value. And if there is a batch normalization layer, then we can directly calculate the importance based on the batch norm weights and bias. With this kind of score calculated, then the typical way to prune the model is going to prune them iteratively until we reach the target. In every single pruning step, we estimate the neuron importance, rank the neurons, and remove a certain number of neurons that are least ranked. Then we fine-tune for a few of iterations to prepare for the next round of pruning. After reaching the final stopping criterion, then we just continually training the model that has been kept for the accuracy recover. Okay, so that's all the basics about the channel pruning. And most of the existing work actually try to address the network pruning under some limited compression ratio. But remember at the beginning, we mentioned that the need of extreme pruning when it comes to the large model, right? So here we are going to talk about more about like how we can achieve it effectively for large compression ratio. There are actually a couple of challenges when we do large pruning, like try to reduce the size by over than 6%. The first one we can see here is that the accuracy of the model will degrade very quickly after maybe 50% of the size, and even in exponential way. Right. So here is the example of the comparison classification model. And there are a couple of reasons for this. Because, for example, for the saliency-based method, the importance score of this is mostly calculated by the single parameter, and then we calculate the importance of a channel as a grouped one. So it's going to be less accurate when there are more channels to be pruned at the same time, because there will be more interdependence from the increasing number of parameters. And another reason would be like when we increase the compression ratio, the pruned model will getting smaller and smaller size. So the capacity of the model is going to be reduced. So it's going to be harder to train after we prune the model. Here are a couple of options that we can try to address this. The first one is that here we propose to preserve the learning capacity of the model and allow the pruned model, the pruned channel to still able to update its parameters and grow back at some point if it's shown to be important again. To do so, we apply the mask to the weights instead of directly zeroing them into like as permanently. Here, as you can see, if we make the mask to the pruned weights, then in order to make sure that those pruned weights will continuously receive the gradients and update accordingly, we can switch to input channel pruning instead of output channel pruning. Because if we perform the output channel pruning, then for that channel, it will get the zero output as always. And if you check all the modern architectures, the ReLU layer is always applied as the nonlinear one. So if you take the output as zero, then the gradients of those weights will get like zero or undefined ones. So it's going to be harder to be updated later. So we switch to the input channel pruning. And now then when we fine tune the model in the following up steps, this kind of weights will be able to update. And once that's enabled, we get the chance to question the optimality of the pruned structure. So what we can do is that after we prune the model, we train the model for a few iterations, allowing the parameters to update, and then we can remeasure the importance of all the channels and maybe get a portion of pruned channels to grow back. So we can have the chance to redo the pruning. It could be possible like for some of the channels after they prune, because the importance score is not estimated accurately. So some of them are pruned mistakenly. So this is a chance for us to redo what we have done wrongly. So another challenge that we would probably meet is that when we do the extreme model pruning by removing the channels, it is highly likely that we can get a model with layers pruned to a certain number of channels that if we set a predefined value, or otherwise, if we do not set kind of value, then this layer might be entirely removed. So it's going to lead to untrainable model structure, or otherwise there will be some limitation on the model size that we can most prove. So we need to consider joint pruning of the channel, layer, and the block for the large prune ratio. As you can see here, if we consider the skip connection in the model, it actually becomes quite easy because we can directly add a layer decision variable or a block decision variable to decide whether we want to keep this layer or keep this block. So here, as you can see, we add 2 more variables to the pruning problem, and then we jointly optimize for the channel, layer, and block decision variable under some certain constraint in a global way. And we use a convolution layer as an example for a better illustration. Actually, this can be also applied to like transformer layers to get some variables for number of attention heads, embedding size, or the size of the query key, etc. So it's going to be extendable. The other thing that we need to consider, especially for some mobility applications such as autonomous vehicle, which requires the real-time response, we need to actually maximize the GPU compute. So this is also mentioned by Jason, like on GPU, we have the instructions executed by the streaming multiprocessors. And this kind of instructions will be split into waves. So to fully utilize the GPU compute, we'd better to have 100% occupancy of the stream multiprocessor. And the different kind of GPU architectures will have different number of processor, cache, memory, etc. So we need to adapt our model according to what kind of GPU that we are going to use to maximize the efficiency. Here is a more visual example in concrete, like when we go to the model size, about how the inference latency of a convolutional layer will change by varying the input and output channel number. And as you can see, while we reduce the output channel number, for example, the latency is actually not decreased linearly. So it's going to be in a staircase pattern. In this case, we will not want a layer forced to somewhere in the middle, like here, because there will be better options, like we can keep more channels remaining in this layer to make sure that we get more parameters remaining, but at the same time we do not increase the latency too much. And because this model will get more parameters remaining, so it's going to be perform better on the inference data. And another option would be to reduce more channels. Then there will be a large decrease on the latency. But because we are actually also reducing the number of parameters, but compared to the latency reduction, this might be a good trade-off. So this actually brings the insights to the pruning. So which means that we should use the GPU characteristics to guide our pruning. So here we tried to directly optimize the prune structure under the guidance of the latency. We directly import this kind of latency characteristics of the GPU into our constraint problem. Then the model can be pruned under optimize this kind of this feature. Oh yeah, sorry.
Did you use a special program to create the screen bug?
Yeah, this kind of so the question is like how we create this kind of figure. I think as Jason also show like we have some profiling tools. So this kind of feature could be obtained by profiling the latency of layers with different combination of input and output channels. Yeah, with those options, we can get the profiled latency for all of them. And here we show an example layer from Resident 50 actually. After pruning with different kind of pruning algorithm, how the latency looks like. As you can see, with latency-aware pruning, basically it's considering the latency characteristics of the GPU during the pruning. We get a lower latency compared to the generic pruning. And also we get more parameters remaining. So it's highly likely that our model will get higher accuracy. And more about the comparison results with different kind of pruning methods of the entire model. The pink line here is like when we take the specific latency characteristics into consideration during pruning, and compared to generic prunings, it actually achieves better latency and an accuracy trade-off. And then when we go for soft pruning with a chance to update the model structure, it goes to the purple line here. If we further enable the layer pruning and the block pruning, we finally get the green line. So further boosting the model performance, especially for like large ratios in the right side. Here we show a little bit more about pruning applications in the context of autonomous driving, especially for the 3D object detection. So this is the detection pipeline that we used for our experiment. The model takes the inputs from 8 cameras mounted around the vehicle. Then we extract the feature independently for each image, then transform the feature into the bird's eye view from the 2D space. Then the feature in BEV space will be fed into a shared backbone. Then we perform the detection on the 3D space. In this experiment, actually, we use 3 different kinds of architectures for the encoder and the decoder. One is that we use a compact model obtained using the neural architecture search. The other 2 are the Resident 18 and the Resident 50, respectively. So here you can see, like, as expected, the larger the model, the higher the accuracy, but it also takes more time for the inference. But by pruning the larger models, for example, pruning Resident 50, we can get the curve, like the model pruned to be here with 45% off and 60% off. So compared to directly training the compact model, it's actually getting a better accuracy and latency trade-off as we mentioned initially. So again, like the best practice to achieve a good trade-off between the accuracy and the latency would be like you train a large model and then compress heavily. And we show here some visual detection results comparison, where we use the compact model, then we will probably miss the distant objects or some clean objects. The detection will also be unstable. All right, so as we mentioned at the beginning, when we compress the model, we should also address the trade-off between the model compactness and the robustness for the out-of-distribution data. So what is going to happen here is that during training, we basically train the model on some representative data. When we compress the model and fine-tune the model to recover the accuracy, this is further makes the model fit to the training data. So when it goes to the inference time, there will be data that is out of distribution comes in. So this model might not perform well. An example here is that we can see how the robustness of the Sigma-Forman changes as a function of the model size. We measure the robustness by the ratio of the model accuracy with noisy input and clean input. Oh. Okay. Yeah, the higher the ratio is, the more robust. I mean, the higher the ratio is, the more robust the model it is. So apparently from the figure, you can see the compact model are more sensitive compared to the large model. And again, when we do the model comparison, getting more compact models, the model tends to less robust. So they actually are contradictory goals, but we are able to get a better trade-off if we jointly consider the robustness and the compactness when we perform the model comparison. So here is what we do. In our recent work, we are aiming at robust pruning. To be specific, we encourage the parameters of the channels that are less important to fall into a flatter loss landscape, because when we do the pruning, actually it's kind of similar to make this parameter of this parameter to be 0. So the perturbation of the loss will be calculated by like here in the figure. So when we make the weights to a flatter minimum, then the perturbation of the pruning, the perturbation of the loss induced by the pruning will be reduced. So those parameters will be easier to get pruned. But at the same time, for those kept parameter, we can see if we also encourage them into a flatter minimum, when we do some perturbation to this weights, actually it's also going to be more robust, inducing some like less loss change. So by encouraging the parameters into a flatter minimum, it's actually promotes the robustness at the same time, and to encourage the compactness. So this is how we do the joint compactness and robustness encouragement. And this approach is proved to be effective in our experiment. As you can see, without encouraging the robustness, the model obtained by the general pruning will quickly reduce the accuracy on the corrupted data. But if we do the robustness pruning, then the robustness of the model is like greatly increased. Now we have all these techniques introduced for model comparison. Like we have quantization, NPM pruning, channel pruning, and even involves the channel, the layer and the block. Now we need to put them together to achieve the most acceleration that we can get. The common approach is to apply these techniques sequentially, which will be like we train a model in FP32 or mixed precision. Then we do the coarse pruning to remove the layer, channel, or block first. And then we do some fine tuning to recover the accuracy to make sure that we can do following up NPM pruning. And then by NPM pruning, we also need another fine tuning process to prepare for the following up quantization aware training. So this is going to be very training cost, like in a large training cost, but it definitely will lead to actually like high accuracy. But we think like a better practice to this is actually to do a joint pruning and quantization at one step. For example, if we can jointly consider the quantization and channel pruning, then we can actually make sure that these two methods complement each other, and we actually consider them in a global optimization way, because if we optimize the network by taking care of them at the same time, the solution would be obtained from like you can have multiple choices at the same time, not directly optimized for certain kind of compression technique. So, and at the same time, it's going to be reduce the training cost. Yeah.
When you're fine tuning after pruning,
Mm-hmm.
do you fine tune on the whole data set or the part of the data set that is sort of giving you lower performance? What is the intuition for fine tuning after?
We actually, in practice, we typically just use all of the data to fine tune the model because I think like that will lead to much better accuracy actually. We can, I think like on the representative data, it's just lower accuracy as you highly likely to overfit to those data. Yeah. Yeah, so actually I think that's all I want to talk about. So yeah, any questions for please?
Any questions from Mayin? I think there are a couple of things that are critical that Mayin said. Train large, compress heavily, and make sure that when you train and you compress, you're gonna be losing this generalization, right? I think that's something that sometimes we don't pay attention to. When we want to deploy the models, we want that they generalize as much as possible. So the last part I think is very, very, very interesting. Please, just any question from Mayin? Please,
Yeah, so normally you can use L1 organization to do like unstructured pruning, right? Is there a similar technique that can also be applied for two sparsity? That's it. L1 to situate that also more sparsity is that possible?
Yeah, I think like so I think the question is that whether we use the regularization-based method for the NPM pruning as well, right? To be honest, if there are different kind of ways that you can do that. You can also directly based on the trend parameters, the magnitude of the trend parameters. That would be the easiest way. Of course, I think like for some of provided implementation, that would be the solution, I think. But if you implement your own, you can definitely also try to apply the regularization like constraint to the single parameters, or you can also use the saliency-based method. So that's kind of different options for you. But I would say using the saliency-based method with some importance, that would like importance calculated from the loss change induced by the removal would be like better accuracy.
Oh, so you can see the base enough doesn't guarantee that you have sparsity, right? Again, if you just prune based on some statements and that just structure mixing application.
Yeah, it does not, but you can compare the importance for like among each of four. So in that case, you can guarantee. Yeah. Okay, thanks.
The fine tuning seems really similar to dropout in a lot of ways. So have you considered introducing that at the pre-training step to save on overall training costs?
Sorry, say again.
If you just use like the fine pruning during the initial training instead of something like dropout, because they seem kind of analogous. Couldn't you save on the overall training costs that come from having to prune and then retrain?
Yeah, I think like from the training cost point of view, it definitely will like save a lot. But from the accuracy point of view, it potentially like you will induce a lower accuracy because every time if you perform the fine tuning during the training process, it's highly likely like your model cannot learn well on the data because lower accuracy again, right? So that's if that answers it.
The last question, please. Can you explain the calibration data in post-training quantization?
Oh yeah, so for the calibration, it's actually trying to get a distribution of the activations, because when after you train the model, you just store the model weights. So you can only quantize the model weights given those stored checkpoints, right? So to improve the efficiency of the inference, it's better that you can also quantize your activations. And this calibration data is going to estimate what kind of distribution of the activation could be. So that can give you some scaling factors, for example, to see how you can quantize your activation. Yeah, so mostly for the activation quantization. I think the common practice is just to select a subset from the training data. That would be enough, because if you random select, it's going to be present the original distribution most in a high level. Yeah.
Okay, let's please thank Mayin again.
Thank you.
Thank you, Mayin.
Last but not least,
Well, again, it's I gotta ask
You wanna help
clear about that.
We
clarify. To the outside user, TF32 is the same size. Inside the system, we actually do convert it to a 19-bit representation for speed of the hardware.
Thank you. Yeah, because I noticed in the docs that it was saying it's actually a 19-bit structure. So
right to the outside world, it's happening internally. So it does the math, it converts it, does the math, converts it back to 30.
good catch. So while we prepare the last presentation, it's gonna be Danny. He also joined NVIDIA a few years ago. If you think about what is happening, right? So Jason is talking about hardware. Mayin has been talking about COMNETs deploying of more traditional computer vision networks on the edge. And now Danny joined a few years ago, working with us on these topics, and he has been moving with all this trend of the very large models, VLMs, LLMs, and more recently they released these VLA amazing models. So he's going to talk to us how that does work and the latest trends and how can we accelerate those models and usually show them what happen. So please welcome Danny.
I need to give him access. So yeah, then you can.
You will show anything.
No signal.
No. That's working. Okay. Is it screen sharing? Yeah.
No screen share.
No, not here. Just yeah. Good. Is it working? Yeah.
I think so.
All right, good afternoon, everyone. Yeah, My name is Hongxue Yin. You call me Danny. I'm currently with NVIDIA for roughly 4 years, slightly more than 4 years. And today I will introduce some slightly research trends, which is I'm going to focus on efficient vision language models. And before I start, I'd like to emphasize I do have a runtime live demo here. So this is a very large 13 billion checkpoints of vision language signals running real time on NVIDIA Jetson Nano that we recently announced at GTC. So after the talk, feel free to come and try the demo here. So basically, it's completely running on that small box over there. That is the key driving force for autonomous vehicle, for the future humanoids, for all the robots. So you can think of like the robot dog has this kind of a central computing units standing on top of it. And in the future, we're gonna enable all these kind of new foundation models onto it. And on the top, you know, it's constantly flashing because the model is running at a pretty high frequency. I will start with the motivation of the recent trends. So as the model really gets pretty larger and larger all the time, right? But we do have substantially varying of computation budgets. For example, for AV, we need one platform. For data centers, a completely different scale of resources that we have. So, and nowadays at GTC, NVIDIA also announced like a huge initiative called GR00T, where we target now into the robot landscape. And recently, iPhone, like Apple, announced this kind of a new support for large language models on their mobile platforms, which in the very near future, a lot of foundation models going to run from the server to the edge across different scenarios. And that you know, motivates the talk. And this talk, we're gonna focus on multi-modality large models, starting from how we train these models, and then how we can do proper tricks for them to be able to be running inference flexibly on these different hardware. And finally, I will share some of our very recent research insights actually from last month that we extend further the functions of these large models. The talk going to be oriented from 2 papers. One is called VILA on pre-training for visual language models, which is we're going to present this year at CVPR, and it's going to be at Friday. I will put the details of the poster later. And then we will go to XVILA, where we extend from visual language to video, audio, image, language, both understanding as well as generation via connecting all the encoders, decoders around the language model to support end-to-end perception as well as generation. Without further ado, we'll jump to the first paper, first project, which is called VILA. So hopefully by the end of this talk, I will allow the audience to, you know, try these models from NVIDIA. I like to highlight this entire project is open sourced from the code to checkpoints to everything. So feel free to run these ones in your experiments, etc. So the first author, gonna be here for the poster. He's now at OpenAI. So this is a joint research between NVIDIA and MIT with Professor Song Han's lab. Song is also here. Yeah. Okay, so what is VILA? VILA stands for Visual Language Model. And the key idea is we want the large language model to be able to see. So that's the focus of the talk. How we do that? The trick is fairly straightforward. We treat visual signals as a new language and feed it into the language model and let the language model adapt to this new type of language and how just learn using extra new data to moderate how the visual tokens will interact with the language tokens. So this is a high-level overview of the architecture. So you can think of visual feature is taken from this VIT, which is a visual feature extractor. It get the output visual tokens and then concatenate these visual tokens before the language tokens. All of these stuff is then feed into the large language models together. So the language model process all the information and alter regressively, depending on the user prompts, will give you the desired output. Through this talk, what we want to show is through a proper training recipe, which what we found is more important than architecture. We observe VILA really unveils quite interesting capabilities, such as multi-image reasoning, in-context learning, visual chain of thoughts, and more importantly, really, really amazing world knowledge, because all the visual signals is now sitting around the large language model. And these models have really superb understanding of how, the general rules are in the human world. And it brings these kind of capability direct to visual applications in zero-shot manner. I will show you later. We observe Vila outperforms state-of-the-art models, open source models actually, such as like Lava 1.5, 1.6. And I will later show for video applications now we are very close to the GPT-4V level. And the good thing is the entire Vila pipeline is quantizable. It's end-to-end quantizable using AWQ. It runs really fast across the media stack of platforms, as I will elaborate later. Okay, so to put long story short, Vila constitutes three major findings. They are our understanding on large language model, our understanding on data structure, and our understanding on data blending. So for large language model, the biggest question is how we should train them. When we augment, we have these pre-trained gigantic large language models, and we want to, augment it towards language, towards image or visual signals. So how should we do that? We observe freezing the language model during this process and using, for example, PEFT such as LoRa or like visual experts, adapters are not that sufficient. So we observe it's really necessary for us to open the large language model. And so opening, freezing them can achieve quite decent zero-shot performances, but as the task of visual language become more complicated, these kind of limitations start to emerge, especially for in-context learning. So as we show by this table here, we had a very detailed ablation in the paper where we compare for pre-training for SFT, whether we want to lock or freeze the language model versus, we completely just open it. And the results is quite strong, where we just rigorously compare all the different benchmarks of visual language tasks and observe, for few shot, this unlocking brings significant benefits. So as we unfreeze the language model, people, the most common question or intuitive question is, will that diminish the capability of the language model? Because the language model is pre-trained, now you tune it towards, visual signal, how will it forget previous knowledge? So it's here actually. So the interesting finding we found is actually the language model only slightly forgets, but the memory is still there. It can quickly pick up the language knowledge as long as you reblend some high quality language data in the SFT stage, which is supervised fine tuning. In our experiments, we only use 1 to 2 million of high quality language data during SFT. And we observe the language model quickly pick up its original strength in terms of language-only capability, as we observe here in the language task, which is very strong MMLU accuracy. But if we don't do that, it's gonna cause us quite strong degradation as expected. The third one is on data structure. So by data structure, what we mean is what type of image language or this kind of visual language signal that we need to feed to the model such that the model can learn. Normally, if you look at current literature, the most widely adopted paradigm is actually image text pairs. So what we do is we give them the image, give the model image, either we give a caption or QA tasks or some perception or understanding tasks. But what we observe is actually a more enhanced data architecture, which is what we call interleaved data architecture, is stronger. By interleaved, we mean there are multiple images along with multiple text in the entire input to the language model during training. So by learning how these multiple images interact with the corresponding text in the middle, the language model can understand some underlying mechanism between different images. And now we are able to run the model for a multi-image task, as I will show later. For some scenarios, a single image may not be able to answer the question. That really requires, to get images from multiple visual sources for you to make a final decision. So to acquire that capability, the interleaved data structure isn't necessary. Okay, I've touched the really high-level understanding of the three findings we have from Vila, but please refer to the paper for details. we have very detailed comparisons there. Okay, I will show some quick examples, and all these examples are online, so you can run at the end of the talk. I provide you with an online demo that is interactive. You can try to see how the model perform when it will hallucinate, all these kind of feedback. Feel free to send us updates, and we will enhance the model accordingly. So if you look at this task, right, the input to the model is a context that is shown to the left, where we show the first image, tell the model it's 3 pandas. Second image, show the model is 2 dogs. Then we only show the third image and ask the model, how would you think? So this is a very normal human-like study process where you gave the student, for example, some quick examples and then ask them to follow the style, generate something for my new future inputs. And that is the in-context learning counting capability. The model is very accurately generating, okay, now it's a cat, and there are 3 cats in the image. Similarly, we are from NVIDIA, so why not bother, like we try some of the different company logos. So what we do is we feed, for example, Google's image, say this company is famous for search engine. We show Microsoft famous for OS, and we show Apple is famous for iPhone and iMac. We prompt with NVIDIA, it is very accurately saying we are very famous for our GPUs, which is quite what we are proud of. Okay, now we have an interesting task where I can slightly elaborate a little bit more. So this is a multi-image task. You look at the image on the left, it's kind of what the iPhone or a smartphone is understanding at a bar table. And the task is giving what you have on the table and give me the menu, how much shall I pay? So that's the overall task. The task is pretty challenging from twofold. First, the model needs to understand what's going on this table. Then it needs to match very accurately the corresponding price of these individual items on the left. And then only given these 2 information, we are able to generate a very accurate output answer. So the question is, we feed, for example, this is the photo, this is the menu, how much should I pay for all the beers on the table? And the model is able to see, okay, the beer on the table is Magna, and according to the menu, it is priced at $6. Then there are 2 bottles of beers, and now the overall price is $12. So you can see the way language model gradually solve this problem based on the visual feature. So this is a quite appealing property. Hello? Yeah, this is can you guys hear me? Yeah, this is quite an appealing property for visual tasks, right? Because this kind of reasoning capability was kind of backed by language model, and previously, sometimes it's pretty hard for like convolutional neural networks or like normal visual transformers to tell like how we reason across these inference steps. Okay, this is how Villa performs on synthetic data. So this is the DALL-E generated images. Note that in the entire training process of Villa, we only trained on real images. But it turns out it really transfers and generalizes pretty well. That means the model is somehow robust to the visual feature as human does. Because as humans, we are able to see, right? This is like a very funky meat-based image. Like it has a lot of delicious hams with pigs and like birds on the sky. It turns out the model is also very robust. It can generalize to these situations. It can describe it in a highly detailed manner. So that's the takeaway for Villa on synthetic data. By the way, feel free to ask any questions during the talk. Like, I want to make it as interactive as possible. Okay, now how does it translate into real-world applications? So what we do is we train Villa on normal data sets and then transfer it on some very zero-shot task cases on the real world. So as we know, self-driving car is a pretty challenging task. Like we train on tons of data, and for the model to understand some particular traits, we need to have a huge ton of labels for that very spatial scenario. And as what we show here, this type of scenario is quite unusual. Like you cannot have a ton of these kind of scenarios on the highway. And this is, you have a flying chair from the previous truck. It's gonna likely to hit you. So how do you perceive this situation? It turns out these kind of unusual detection is a very strong traits for visual language model. It is able to understand, this image is kind of behave slightly different because the unusual aspect of this image is the chair is flying throughout a truck on the highway. And what should you do if you encounter this? So the logic reasoning of language model again kicks in. It says like, if you encounter this situation, you should immediately stop your vehicle and move to a safe distance. So it's kind of a really good and strong add-on to visual task because it even gives recommendation of the corresponding actions to the visual input. Similarly, we also try to see if it is able to understand some historical data. So this is a data we took from the web indicating the Arctic Circle. It's from a satellite. It has some text in it, like from different years. So the question is, what is the implication of the temperature on this image? It's a very indirect prompt, but the model is very actually going to reason through it. So it says like this image shows a comparison of Arctic cover from these roughly 30 years. The implication is roughly due to climate change, global warming, and what's the implication of this warming to the world. So this kind of knowledge, is pretty strong. We also try to show some kind of healthcare application where previously for quite many domains, right? Like medical is one of the important things that computer vision can really, really help. So the unusual thing about this image is we deliberately select, one image with a fake person. So if you look at the person on the left, right, it's a fake one. It's not supposed to be painful. So we want to trick the model and see how it understands this situation. First takeaway, the model is able to answer very professional answers, like what is this training session about? So it is able to get this CPR output, and it is able to tell, this before this session is on the mannequin. Will this practice cause pain to the patient? Okay, the model understands it's a mannequin. It's not supposed to be painful. So it's a normal training session. And so this kind of, it helps, for a normal surveillance task or other kind of recommendation situation because it understands these kind of complex parts. Okay, I've shown lots of demos. How about quantitative comparisons? So we compare Vila across other, not only open source. At that time of submission, we compare most of the SOTA methods for 12 different benchmarks. Actually, in the latest release, the entire team, we are actually maintaining the Vila repo. I will show some later SOTA results later, but this is at the time of submission. If you look at Vila here, right, just by improving on how we do the training of these models, we were able to beat most of the previous work by quite some noticeable margins. And this is not even for multi-image, multiple images. This is single image text task. We're able to surpass most prior work. Okay, the good point. Everything is open source. So what we discussed today, the model, the checkpoints, the code, they are open sourced. I will later show you guys the corresponding link for this repo. It's called Vila repo. We actively maintain on it for all the recent updates. We also support a very entire family of Vila checkpoints from 3 billion checkpoints up to 40 billion checkpoints. So all the checkpoints are paired. We have a full precision version. We also have a quantized version already open sourced. And we rigorously profile Vila across entire NVIDIA platforms. Okay, which is not shown here, maybe in the next slide. Okay, so now Vila supports both image as well as video for the benchmarks. In terms of the competitive landscape where Vila stands, Vila is currently now the best open source models. So this is the very amazing benchmark, MMMU, which is the multimodality leadership board. So now Vila is, so the group, the red parts are open source models, and the blue ones are closed proprietary sources. We rank among the highest for all the open source ones. Okay, now I will show more demos for the very recent results we got in VLA 1.5, which is for video understanding. So because we support multiple images intuitively, as well as what we show heuristically, now VLA supports a very comprehensive understanding of the video signals. Okay, let's do later. Okay, so the video here shows, okay, according to this video, what will happen next? So it requires some kind of inferring capability, and what the model says is based on the video, it is very likely the next steps is we want to blend the strawberry in the blender. Similarly, we asked the model like what might be the next steps according to this video, and the model says, okay, next step is very likely you'll place the dough on the baking sheet and bake it in the oven. Similarly, we give the model this video as well and ask what will happen. It says like we will likely grind and mix the ingredients together. Similarly, so for sports, it's very exciting moments, right? And then we asked the model to, for example, caption this video for us, because there are many videos in the wild that miss this kind of information for future alignments. The model is able to generate a very accurate caption. It is able to describe there's a goal happening in this process. The ball goes into the goal, and you know the players celebrating with all the teammates, and they hug each other. This is for self-driving. What's unusual about the situation? It is able to say it's very foggy, and how you should react accordingly. So I think there is even an audio associated with it. It is basically able to reason based on these kind of based on how the finger moves and detect where you are on the different notes, and based on that, it's able to deduce all the MCQs pretty accurately. Okay, to be more precise where we are. So for video benchmarks, the open source VLA model is now very close to GPT-4V. If you look at the quantitative numbers here, overall, so GPT-4V is roughly 59.9, and we are now 59.0. And good thing about this model is you can even go home today and try the model. So it's open sourced as usual. Now, I described how we train the model, what the model can do. Next step is how we really run them, right? Like these kind of models are so huge, it's like easily 20, 30 billions of parameters. How should we do it? I will try to make this one as less researchy as possible because it's a tutorial. I really want everyone to be able to use it. That's why I would mainly show the techniques behind it. I will not delve deep into how it goes, but mainly show some kind of high-level review. So the entire VLA family is now end-to-end supported via NVIDIA TensorRT LLM. And the technology is very similar as well as to the AWQ, which is from MIT. So the AWQ just won the Best Paper Award at MLSys. It basically conducts 4-bit quantization. After the quantization, we are now able to run VLA across the entire stack. So if you look at what we show here at the bottom, it is supported on A100, H100. It is supported on 1490. It is supported on AI PC, as we will have another PC demo here. So it is disabled from the internet, but it's still able to analyze all the images. And we have the Jetson Nano live demo here as well. If you look at here, right, on the right, so this is the real speed of different platforms. We have A100, 4090, Orin again for server, desktop, as well as on the edge. And the speed is like tokens per second. For all the normal rows, so this is full precision, FP16 checkpoints, and AWQ means this is the quantized checkpoints. So all these checkpoints are fully open source. Feel free to try them, feel free to download them. Actually, since we open source, the model has been downloaded like roughly 2 million times already, where we observe a very huge welcome by the community. Okay, this is a live demo on Orin. Actually, I can also show here. So this is how the terminal interface looks like. We just, add a corresponding demo because Orin is able to also drive external devices. But if you look at the speed, it's pretty amazing. So the user asks, like, what is the unusual in this image? So this is the speed that it generates. There are several deer crossing a roadway. In this case, the deer maybe, is pretty risky. We should protect the deer. And shall the driver honk at the animals and why? Then say it is generally not recommended to honk at the animals because they may be panic and cause a lot of danger to this situation. So this is the live Jetson demo. The model is in the Jetson library. That is the NVIDIA official tutorial blog. So it will give you step-by-step guidance on how to run our visual language model onto the hardware that we announced at GTC. Okay, so this is a demo for Vela on GeForce. The speed is much faster. And the problem we see here is exactly the same as Gemini. The question is, based on this image, which car is more aerodynamic? So it requires some kind of abstract thinking, right? Like the car is going downhill, one is more streamlined, the other one is pretty boxy. So is the model able to tell this difference? And it turns out the answer is yes, and it's able to do this inference very quickly. You see, it basically immediately pops up the speed with the very accurate answer. The speed is roughly 10 milliseconds per token. This is a demo on AI PC. So this is entirely run just on this Apple computer without any external server access. Yeah, the pre-filling takes some time. But yeah, now we can run the model. Yeah, this is actually on CPU, right? Okay. Now I will slightly touch upon a very recent work after Vela. Now feel free to try Vela, Vela was done by amazing research intern at NVIDIA. So now what's next, right? Okay, the slide is timed quite weird. I may actually use the raw one. Can you guys see it? Yeah, okay. All right, so basically on Vela, right? What we study is we now inject visual features quite accurately towards the language. But what's next, right? So in this work, we basically take one step forward, how we can even extend from image into more different types of signals. So XVela is the real effort towards the connection for 4 different modalities. And by 4 modality, we mean video, image, language, as well as audio. So through the development of XVela, now we show a bunch of quite excited applications down here. Now we can do image language demo. For example, what is in this image? The model is able to show it's a beach with a sandy shore. It now can also do language to video generation. Can you make a similar video with people in it? Now it drives the downstream diffusion models to give you a video output. Then based on the video, are you able to generate the corresponding audio for it? Then it calls upon the downstream audio diffusion models to generate the corresponding sound to it. And then what is about the video to image? It also connects all these very promptly. So we also do, if you look at all these different types of modalities that enable what is in this video, what do you think is gonna happen? So it will synthesize this snowman taking the ski after it polishes his ski. So it is able to also reason across the temporal information for what's gonna happen next. Interestingly, we observe some zero-shot capability as well. So just give an image. Now it is able to generate some sound. Give me an image of dog. It generates the dog sound. And if you combine with different information, it gives you a new generation. So down below here is some extra interesting observation that we show. So previously, what we think of is diffusion model can only take one or two very simple modalities, right? So what we show is now through XVILA, we can perceive across modalities to drive a single modality pre-trained diffusion model. So we give two modality inputs. One is the image of a park. The second one is a video of a girl, and ask the model to generate something that combines the elements of both. So the model is able to generate a girl walking in the park, and it is further able to generate the corresponding sound for it. So I will not touch too much on the architecture details. It's just being announced. But this is the high-level overview of what's going on. So basically, we align encoders from different modalities to the input of the language model, and then we align the diffusion model decoders to the output of the language model. So the key actually is how the architecture going to look like and how to train this model. In order to answer these two questions, we first conduct a very comprehensive study on how we do that, and we found similar to Vila's streamer work, we project everything into the large language model space. So all the extra tokens are one extra type of language. It will be fed and jointly learned by the large language model together interactively. And then when the language model feels, okay, I need to generate something, it will generate some like alien language that will be later reprojected to the corresponding diffusion model decoder space. Then this language will be understood by the diffusion models across different modalities down the road. So through their joint training process, which we highlight quite rigorously in the paper, now the model is able to both understand as well as generate. Some qualitative comparisons. So we compare with at that time current best open source models that supports cross-modality understanding. I think most of them. And this is the very recent GPT-4o. So bear in mind, GPT-4o, when they release it, they support perception of cross modalities, but the generation is not yet supported. So what we do is we call the special requests of GPT-4o and generate these kind of images. So what we do is XVILA is able to achieve quite stronger, improved visual consistency because of visual highway architecture we introduced in the paper. I will skip the benchmarks here. It's just some quantitative analysis. And at the bottom is quite interesting. Throughout the entire training, actually, we didn't prompt the model with these kind of audio visual signals. And these kind of behavior starts to really emerge after we do the alignments. For example, when you give the model a baby laughing, it will give you the image as well as if you give the audio, give the image, it will generate the audio. So all the modalities can now talk to each other and work with each other. Since we're in Seattle, it doesn't make sense for us to not try something for Seattle. So this is what we achieve with XVILA. Bear in mind, all the things you see here are synthesized. They are not real. They are generated by the downstream diffusion models. And this is a very long chat. So the model, we are prompting the model accordingly, like, hey, I'm temporarily moving to Seattle for the summer. Do you know any nice place? And it is able to get the Space Needle and recommend some good food and then correspondingly generate the overall scene in the video form. Sorry, I cannot play it here. But yeah, that's a video. Okay, quickly. This is resources. This is a QR code for the online interactive demo. So if you want to try it, feed your own image, feed your own prompts, try these resources. So these resources support video tryouts. It also supports multi-image inference. For the exact prompts, right? When you feed multiple images, try to follow the examples that we show on the right. So normally that's the best way to try on different downstream tasks. And yeah, now we are on the last slide. Yes, so this is all the useful information. I will just leave the slide here. So the Villa paper just recently released. The QR code is there. It's gonna be in June the 24th or 21st. And it will be the Friday afternoon session. So the first author and me, and actually some extra PhD, for example, Hans Hai, we are all gonna be there. So look forward to discussing details if you have any more questions. X-Villa paper is it's still a preprint, so we just released it a month ago. So the code is the QR code is here. At NVIDIA, we have 2 official blogs at the time of GTC, actually, when we launched this interactive demo. And feel free to try understand the big picture using the upper technical blog and try to go through the tutorial with the detailed how to run JSON on the left. For the code access, and if you really want to, for example, download the model, run the model through command line on the server, so this is where we will constantly maintain and update. This is a new repo, actually. We have a previous repo, but now everything gonna be here. Okay, with that, I will conclude my talk.
Thank you, Rami. Questions? I'm curious. I want you to show something more than.
Yeah, I mean, so the prompts, the default prompts I key in there, we put in there is describe what you see precisely. Because if it is too long, then because the model runs really fast, it will just disappear. But this is a camera that is also driven by.
So you think it's possible to share the screen?
I don't know, actually.
I mean, to connect the USB-C here, so
to where?
Directly to the
maybe to the projector, because that's a projector as well. So.
Sure, you can do that.
Connect to Zoom and share screen.
Yeah, that's what I think. So if you connect it through this one, we can share the screen directly.
Oh no, but that screen is driven by JSON. It's not so that's not a computer. It's purely driven by, it's just a screen driven by the Nanobox. Yeah, normally just come to it like I prepare some toys. You can ask, you can check like.
If I can hear, what do I see?
Okay, so if you go there, you're gonna see a live camera. So the live camera is where the model is seeing. Entire model, everything is driven by that small box that's a JSON Nano, official from NVIDIA, and just take from this camera and it will start to describe, because the default prompt is describe what you see. Yeah, you're a polite guy. Yeah, that's what it says. It constantly refreshing on the screen what it sees. That's the text outputs. I think we will likely set another AI PC demo here somewhere. Yeah, just feel free to come chat and play around. Like, yeah, we can also key in different prompts if needed. Yeah, that's another. Or I can first answer some questions, right? Yeah, please. Yeah, feel free. Can you repeat again? Yes, you can. So that's kind of an orthogonal approach, right? So for the Villa family, we support varying type of language models. So if you look at the language model support, we support Llama 3, we support Shared Llama, we support Llama 2, we should support Vicuna, we support E34B. So this entire one is assuming you have the language model already, and then you augment it towards vision. So the language model can be KD augmented, it can be any type of strong language model. So after you train for language, now just do it for vision. Yeah.
Thank you for the presentation. I thought that the projector, I thought that the linear layer is better than the transformer. So can you expect for this, should we continue to focus on this?
Okay, that's a good point. So actually we found the projector is not quite significant as long as you open the language model. You can think of when you connect the projector, we tried different types actually. In the paper, we show transformer as well as linear, right? We also try MLP, we also try convolution. Actually, in the paper, we also discuss if you use stride2conv, you're able to reduce the number of tokens, right? You can shrink the number of tokens if you do stride there. So what we observe is if you lock the language model, then the choice of linear projector actually matters because by a stronger reprojection, you have a larger hyperplane to support these kind of new modality, right? But as long as you open the language model, that's a billion scale language model. It will easily absorb whatever difficulty you have here, as long as you have sufficient mechanisms of pass the information here and learn everything in the language model space. So I would say we will not say linear is better than transformer, but ideally they are very similar. So one's relatively on par. Yeah, please.
So you mentioned there are 3 input modalities that go into the model: audio, video, and audio, language, and images.
As well as text 4. Yeah.
Okay, cool. And you mentioned that you use interleaving. So what exactly does interleaving mean? Like when you go through the iteration, you only use like some subset of these modalities going in and not all of them every time?
Yeah, that's a great point. So that's basically when you do, that's the discussion point of XVL. So when you do more modality interleaved, it's slightly more trickier. So that's what we argue for. We took these kind of inspiration, like what a human does. We took it from video. So give a long video, it's a very fertile resources for image, video, as well as audio, as well as text, because you can easily caption the corresponding video chunks into text. So now you formed what we call mother data sets that gives you each video chunk, you have 4 modalities. Then you can sample them into a different interleaved manner and use different modality, like you sample something here to predict the future ones. So that's how we construct the interleave for multimodality. Yeah.
Thank you.
Yeah, please.
Like Meta recently released a chameleon, right? Early fusion, like they do early fusion and joint encoder training. So what are your thoughts on comparing this against that kind of approach where in the pre-training itself is multimodal?
Yeah, that's a great question. So the recipe here, I think, is a very vibrant research field. Different companies have different approaches. So if you compare with, if you really compare them, right, it's basically, I would say, in a way, training resources versus final quality. Like if you have tons of data, then you can basically try, for example, you blend everything together from the very beginning. You can even train everything, starting with a language model, mixing together, right? So exactly how we did it, I mean, how different companies are doing it, that's kind of the proprietary information nowadays, isn't it? Right? Yeah. Yes, we do SmoothQuant, we do GPTQ, we do AWQ, and actually we found the TinyChat works the best. Yeah. Yes. That's a good question. Actually, personally thinking, I think it's really other modalities want to leverage the strength of pre-trained language model, because as what we showed by ChatGPT, right? Those language models are really well trained. It has those sense of emergent knowledge, right? If let's say in the future we have a super strong world knowledge in a video foundation model, such as Sora, right? Or like Sora plus, then maybe other modality will be reprojected into the video space. Who knows, right? So I think that's just a kind of a meta paradigm where it's very beneficial to orient your stuff around the strongest point where you can extract knowledge from.
So it's very impressive. Like from like my intuition or from what I get from this is you pretty much can solve. I don't know. For example, autonomous driving uses, right? You have get NVIDIA to build the hardware to have this 30 frames per second or even faster, and you're and intelligence going to go through GPT-4. So what is it? Is there what it cannot do anymore, right? What are the challenges? Yeah, I don't see how it cannot succeed.
That's a great question, right? I cannot disclose too much information, unfortunately, but let's talk from a research point of view. So if you go through other workshops, right, at CPR, I was hosting the other one, which is Efficient CV workshop next door. But there are many AV workshops recently. You can see many amazing works on applying vision language model for driving. Actually, I think news came out 2 to 3 days ago. These vision language model is now running on XPeng in China. Like they really deploy the drive VLM models onto the real car to make decisions to understanding the scenario. And with regard to what NVIDIA are gonna work next, just stay tuned. And then yeah, we'll probably announce later. Yes, please.
What are your thoughts on the way we evaluate the language model for the right
That's a great point. So that's why when we do VLA evaluation, right, we basically exhaust whatever public evaluation benchmarks that we can find. But even with that, we still found the way we have these value benchmarks are not satisfactory. In fact, if you look at the benchmarks that we do it here, one of the benchmark, which is this MMMU, right? They're gonna discuss it at this year's CPR. The authors are here. We briefly chatted. It's quite interesting. They are also the award candidate paper. I would say it's a vibrant field, how we evaluate for different scenarios and how we, especially as more modality come into play, it becomes more challenging to evaluate the models. So I would say the best one is deploy and let the society tell. Yeah, please.
I don't know if it's not video evaluation, but a few of the examples you showed from the evaluations, like, you could do a lot of them just from like the last frame, the middle frame, the first frame. You know, if someone says strawberries in a blender, just the image of that and say what's going to happen next.
That's why we have to run a lot, right? For some tasks, you cannot tell by looking at a single frame. For example, for some of the video tasks, it asks you to generate the frequency of the waving hand. It asks you whether the man is going left or going right, because they ask you some questions on the periodical signals. So there will be benchmarks associated with those different pain points. So what I see is the research field is moving very quickly. It will give you different types of benchmarks for different traits. So ideally, your model should have good performances across the benchmarks in order to exceed and propel. Hi, Jay. Mm-hmm. Yes. What I can disclose is in the paper we report MMC4. What I would recommend is any kind of real human formed interleave data, for example, on the web, will be good resources to learn this kind of intelligence for interleave data. Yeah, so what you see there is basically the real life demo. Oh, how did you guys do it? Okay, it's quite interesting.
My Ying's laptop is looking at the screen, and then I'm showing the zoom from my Ying's laptop looking at the screen.
Yeah. So if you come closer to the demo, yeah, I think it's. Yeah, you can't even read my name. Yeah. Yeah. So basically, this is a live demo. I think just when you come here, this screen, the green parts is a prompt. So basically, that's what we are running to ask this model here to answer. And the white one here is the real-time answering auto-regressive generation from VLA. And this is an 8 billion Llama 3 checkpoint version where we augmented with the visual signals. Yeah. So what did you do to bring the model to the? That's the tutorial. Sure.
You want to grab the basketball?
Yeah, let's see. Let's do a basketball. Okay. Yeah. Yeah, a man is holding a basketball in their hand. Then we can also try, for example, football. Yeah, a man with a football in the speaker. We can also try, for example, different baseball, right? Yeah. So basically, it's able to react to like real-time situations. If you come here lightly, you can even swap different prompts as well. Like we can use other prompts, like describe the image, then it will be slightly longer in the generation, right? Like if you look at what's going on. Yes. Yeah, you can also ask what color you think. Yeah. Like it's saying like the prompt now is changed into what is the color that this I'm not wearing. Then it's looking at Jason, so it's saying you are wearing a green t-shirt.
In your experiments, have you observed any challenges if there are multiple objects or subjects in the environment and you ask a question, but which is related to complex interactions between them? Like, does the model struggle there?
That's a good point. I mean, feel free to try. Like you can challenge the model. It sometimes can hallucinate. I would say it's not perfect. So that's why I think it's a constantly evolving research paper. Yeah. Even language model. Oh, this is different prompts. Now it's what's color. I can got that. Yeah. So this is described image. Yeah. Yeah, football in the other. Yeah. And read maybe. Yeah, it is able to oftentimes read that text very accurately. It's not very true. Yeah, I'm kind of drinking water, it says, right? So,
And you said Dasani there for a second.
yes, so feel free to play, come and check. Yeah. Maybe after the closing session. Yeah. Any other question? Please. Yeah, please.
How is it running real time?
Oh, so basically it's a JSON Nano. So that's like on the edge computing platform NVIDIA develops. Actually, that's what it runs on the robot dog or the humanoids. There are like I think one on the brain, one on the on the chest, and it is able to drive a external devices. It runs Ubuntu, so we just program it. It runs our model. It depicts everything onto the screen. That's a very simple code that we just wrote for the demo purpose. Yeah. Yeah, please.
Have you tested it for typical failure modes, like I don't know, counting beyond 3 objects or something that it really struggles with?
Feel free to test this. Yeah. Try to trick it. Yeah. Yeah. This is a small model actually. It's like 8 billion one. If you go to larger models, normally it's more robust. Yeah. So the one on the web, we run the 40 billion. That's slightly more capable because the language model is larger. Yeah, please.
I think you mentioned it's running a 7 billion model.
Yes.
And as far as I know, just now has 4 gigabytes of memory, and the model barely fits into it. So it doesn't give any room to it.
What's the memory here? It's like 16 gigabytes.
16 gigs. This might be a 16 gig, and also you said you 4-bit quantizer, right?
Yeah, 4-bit
quantization. So it's 2 to 1.
Yeah.
Or are you a customized?
So this is TensorRT. TensorRT.
Once again, TensorRT, use it.
Yeah, that's what we show. We observe it's very negligible. So we use the benchmark quantitatively to measure it. So yeah, we have all the comparisons on the web. So when you see the models on the left, quantized, full precision, quantized, the right are all the benchmarks you can think of. Yes.
Last question. Okay, let's thank Danny again and Jason for putting together the. So I guess with this, we're going to conclude the tutorial. Thank you so much. Feel free to come and play, and we will put the videos and the slides and whatnot on the web. And of course, feel free to reach out to any of us if you want.
Sure. So great presentation, first of all. Thank you very much. So Marcus, the presentation that you did, the thing I noticed was you had a slide over there with different NVIDIA architecture precision values. And so my question was, there's this one experiment I tried. I was running my own models and I was running on a 20 series GPU, and then I moved back to a 20 series GPU, and suddenly there no change whatsoever. The accuracy changed. It went like 0.5%, 0.5%, either way, different endpoints. So I thought it was some,